The return of Catalan's constant. So the well-known Catalan's constant is here again in this integral. If you don't know about Catalan's constant is this number: 1 by 1 square minus 1 by 3 square plus 1 by 5 square minus 1 by 7 square plus 1 by 9 square, and so on. It can't be written in terms of zeta function or any of such other functions. That's why it is named after itself. And this is also a special case of the beta function, where beta function of s is this expression where the power is not 2 but any general number s, and so g is just beta of 2. So let's see how do we get such amazing number in this. And if you don't know about what this k function is, k is the complete elliptic integral of first kind. That means, let's say if I have k of, let's say, m, then this is integral from 0 to pi by 2 of 1 by square root of 1 minus m square sin square theta d theta. This is known as the complete elliptic integral of first kind. And now let's see how do we get this result. Okay, let's begin. We have integral from 0 to 1 of k of k dk. And we know that capital K of k is 1 by root under an integral from 0 to pi by 2. Sorry for missing that. 1 minus k square sin square theta and then d theta and then dk. So in this second integral, we can make a substitution that t is sin theta. That will simplify these stuffs. If you make that substitution, both of them, this will also now go from 0 to 1. We will have 1 minus k square t square. And if we make t equal sin theta, theta equals sin inverse t, that means d theta equals to 1 by root under 1 minus t square dt. And then dk. Now from dominated convergence theorem, let's interchange these two, dt and dk. So now, but this will remain same because both of them are going from 0 to 1. But now we are actually changing the order of integration. 1 minus k square t square and root under 1 minus t square by dk times dt. Now in the world of k, t is just a constant. So this can be taken outside of the integral. We can take root under 1 by 1 minus t square outside and just integrate the other stuff. And its integral will be sin inverse kt. And since k has a constant t over with it, that's why we need to divide by t as well. 0 to 1 dt. Now if you try to find its value at the given limits, we get 1 by root under 1 minus t square. At 1, this is just sin inverse t by t, and when k is 0, this is just 0 dt. Now how would you simplify this thing? Since there is derivative of sin inverse t over here, a good way is to be like substituting x equals sin inverse t, so that this will go to dt. And if we do this, we will have integral from 0 to pi by 2. Sin inverse t will be x, and dt by root under 1 minus t square will be dx, and t will be sin x. Now how do you simplify this? Now in your 11th 12th grade, you might have seen that if we have such cases, we basically split the sin x into sub-angle formulas and then introduce tan and sec square x and then simplify these stuffs. So this is 2 sine x by 2 cos x by 2. Yeah. And after that, what you can do is basically divide by cos square x by 2 in both numerator and denominator. That will take it to, if we divide by sec square x by 2, we will have sec square x by 2 by, over here this will be tan square x by 2. And yeah, here's the simplification, now here's simplification. Now after this, we will make a substitution that y equals to tan x by 2. If we make the substitution, we will now have tan of 0 by 2 is 0 and tan of pi by 4 is 1. And now x is tan inverse y and then 2 tan inverse y. 2 tan inverse y. Yeah. And then sec square x by 2 will be 2 dy. Yeah. And tan square x by 2 will now be y square. So now, is this the thing? Okay. So this is not tan square basically. If we divide by sec square x, if we multiply by sec square x, sec and cos cancel out, and here sine by cos will be tan. So not really square. I'm sorry for this. This is just tan. This is just y. Fine. Now 2 to cancel out, and so we have 2 integral from 0 to 1 tan inverse y by y. Now this one is doable. So how do we approach this? Now you basically know the series expansion by tan inverse function. Yeah, we basically sum from, okay, sorry, so let me start with tan inverse. The series expansion for tan inverse y is basically sum from n equals to 0 to infinity x to the power 2n plus 1 by 2n plus 1 and then minus 1 to the power n. This is it. Yeah, that means it is x minus x cubed by 3 plus x to the power 5 by 5 minus x to the power 7 by 7 and so on. Now over here also you can use the series expansion by tan inverse function. That gives us integral from 0 to 1 by y of sum from let's say n equals to 0 to infinity of minus 1 to the power n y to the power 2n plus 1 by 2n plus 1 dy. Now let's interchange the sum and integral. That gives us 2 sum from n equals to 0 to infinity integral from 0 to 1 minus 1 to the power and y to the power 2n by 2n plus 1 dy. After this we have 2 sum from n equals to 0 to infinity minus 1 to the power n. If we integrate this, we will have y to the power 2n plus 1 by 2n plus 1 whole square. This is going from 0 to 1. So that's why we will have 2 integral from n, sum from n equals 0 to infinity minus 1 to the power n. Yeah. At 1, this will be 1 by 2n plus 1 whole square. At 0, that will be 0, so it doesn't matter. Now this is the answer. And we see that this sum is actually 1 by 1 square minus 1 by 3 square plus 1 by 5 square minus 1 by 7 square. And it goes on. We know that this is just the Catalan's constant, so this is 2 times g. This is how we got the Catalan's constant in this integral. To talk about the flow of the problem, we first invoke the definition of the complete elliptic integral of first kind and made this substitution. Why we made the substitution? So that isn't there any reason why I made the substitution? What if I did not make the substitution? Would it still be easier? Huh? Oh yeah, even if I didn't make that substitution, it would still have been easier, I guess. Yeah, I realize. If I didn't make the substitution also, it would still have been easier. Okay. So basically, if I didn't make the substitution and the interchanged 0 to pi by 2, that will just be mm, sine inverse of k sine theta by sine theta. Oh, it would be something like this. And after that, I will put k as 1 and then sine theta as y, and again okay, so basically we will get the same thing. Yeah. But yeah, you can try in any other ways. Like, I was mentally prepared for this one and I did this like fine. And then after that, what did we do? Okay, so we integrated. After integration we got this result, and of course this was obvious to make the substitution. Now this is also obvious, and then okay, we got this form. From here we had to use series expansion. Yeah, so that was it. Hope you enjoyed the video. Thanks for watching and look forward to seeing you in the upcoming videos too.